Okay, it's 5 p.m. now in Germany. I think we are ready to go. Again, welcome to our webinar. My name is Victoria and I am your host for today. Before we start, I will give you a few remarks for your information. Please feel free to type in any questions that come up during the webinar in our question box. You should see it at the top or right side of your Microsoft Teams window. The icon is called Q&A or whatever it is called in your native language, and it looks like a speech bubble with a question mark. We will answer as many questions as possible at the end of the webinar, and if there are too many, don't worry, we will answer everything via email within the next days. If there are any technical problems, please don't worry. This webinar is being recorded for you, so you will automatically receive a recording of the webinar within the next 2 days by email. Now, I would like to introduce you to our today's speaker, Dr. Elena Mukina. Elena studied physics and mathematics at the Yaroslav State University and has a PhD in physics. She has been part of the NET analyzing and testing family for over 20 years now, and has gained lots of experience in our R&D department before taking over the position of the business field manager for the software Kinetics Neo. Elena has been a huge contribution to the development of the Kinetics Neo software, which she will demonstrate you today. Welcome, Elena. We are happy to have you here today talking about curing kinetics, measurements, models, kinetic analysis, and process optimization by Kinetics Neo. I will now hand over to you, Elena, to get started. So enjoy our webinar and have fun.
Hello, everybody. Thank you, Victoria, for very kind introduction. And now I would like to start my webinar about curing kinetics. Today, I would like to tell you about everything from measurements, model, kinetic analysis, and the process optimization by Kinetics Neo software, Niche Kinetics Neo software. Now we have agenda, kinetics for thermosets, composites, photopolymers, introduction and workflow at the beginning. Then we have thermal analysis methods for study of curing processes, what kind of methods could be used and what kind of properties must be measured for our kinetic analysis. Then we have kinetic model for curing process dependence on time and temperature. We consider different kinetic approaches, models, including autocatalysis models and the curing with diffusion control near the glass transition temperature. After that, we have some very nice example of time temperature transformation diagram, including gelation and vitrification, construction and validation of this diagram. And then we have a very new part of our Kinetics Neo software is dependence on additional parameter. The first part is dependence of UV curing on UV intensity. Here we will be able to create the common kinetic model, which depends not only on temperature, but on UV intensity as well. And the next part of this dependence section is a dependence of the curing on the concentration ratio of the reactants. Here again, we will create a common kinetic model, which depends not only on temperature, but additionally on the concentration ratio of reactants. And the last part is the simulation of curing process in Thermica Neo software. And now, kinetics for thermosets, composites, photopolymers. Here we have a curing process, and using of kinetics can help us to answer the questions. What is the curing rate? What is the degree of cure at given temperature after given time? What is the state of material? Is it still liquid or is it elastic, or maybe it is already vitrified and has a glassy state? And we here, Kinetic can help us to optimize our production process, industrial processes. The idea, firstly, we have laboratory measurements at different temperature conditions. For example, here is DSC measurement at different heating rates. After that, we analyze this data and create one common kinetic model which can describe all this data for different temperature conditions. Here, for example, we have points which are our experimental data and a line are our model. And we see that this model can describe all experimental data very well. After that, we can use this kinetic model to predict the behavior of chemical system, of curing system at another temperature. For example, for isothermal conditions, for 80, 90, here 120 degrees C. And here we can predict, for example, degree of conversion. We can predict heat flow. We can predict different concentration, and for multi-step reaction, we can also predict the intermediate concentration of intermediate reactants. And here, this possibility can also, this model can also give us the possibility to make optimization of industrial processes. Now, what is necessary to make the kinetic analysis of process? We need a data, and this data usually could be done by thermoanalysis method. It is DSC, it is a rheometer, and this is dielectric analysis, where we can measure the ion mobility of dipoles and how do they rotate under applying of our electrical field. Here, we usually need for kinetic analysis the enthalpy of reaction, Gill point, glass transition temperature, heat capacity, maybe viscosity. And the methods which are used for measure all these properties are DSC, temperature modulated DSC, rheology, dielectric analysis. If you have a possibility to measure some other properties, for example, a concentration versus time, then this data could be also analyzed and kinetic for such data could be created. Now, DSC, we have sample and reference crucible, make heating and measure the heat flow between them. And the heat flow is for the curing process is the curve with the peak, and this peak means the exothermal process, the production of the heat energy. And here we can measure at different heating rates, slow heating, fast heating. And then for each peak, we can create a ratio between the total enthalpy, between the current peak area to the total peak area. For example, here is the current peak area and the total peak area, and this value is our degree of conversion. Another measurement is rheology, for example, oscillating rheometer. Here we have log of shear viscosity. Again, we can make slow heating and fast heating. We have a same baseline before and after measurement, and we have a different curves during the heating. Then for each curve, we can create a baseline for a reactant, baseline for the product, and create the ratio between the current changing of the ion of the viscosity, log of viscosity, to the total change of viscosity as a difference between the viscosity of product and viscosity of reactant. And now we have a degree of conversion. Next one is dielectric analysis. In this case, we measure the mobility of ion mobility of our dipoles. And here we apply the voltage, the alternative voltage, and measure the current and see how our dipoles will be rotate with our changing of the voltage. And ion viscosity is 1 divided by ion mobility. And here again, we can see how the reaction goes on. Usually, the measurements are done with the heating at the beginning, and then it will be at different isothermal segments at different temperature. And here, for example, we have some measured curve at low temperature. It goes very, very slow, and then finally it has a higher value. And we have also the measurement, the curing at high temperature. It goes very fast and finally has the low value. Then for each curve, we can calculate the baseline for the reactant and for product. Then we create a ratio between the current change of ion viscosity to the total change of ion viscosity and have the concentration. And finally, for each method, we have a conversion, and this conversion change from 0 to 1 and show us how the reaction goes on. Differential scanning calorimetry can also provide very good information about the enthalpy of our curve as a peak area and a glass transition where we have a changing of CP and a step on CP curve. And we know that this glass transition temperature before curing is has the lower value as the glass transition temperature after curing. For example, for the second heating, we have a glass transition which is above the glass transition temperature for uncured material. This is DSC. Sometimes we have something like this, and here we have a glass transition somewhere between the inside the range of our curing. And usually if we have only one DSC curve, then it is impossible to find where is the glass transition. In this case, we use another technique, which is temperature modulated DSC. And with temperature modulated DSC, we can find a reversing heat flow, which shows how our heat capacity change with the temperature. And we have reversing heat flow. We can use this reversing heat flow as a baseline here. And after that, we can find enthalpy very well. And we can find the glass transition temperature here for this case. Next measurement is rheology. Here we are able to find the gel point over shear modulus. Here we have a vertical curve is the shear modulus in log scale. We have two components of shear modulus, elastic component and viscous component. At the beginning, for uncured material is liquid and we have viscous component is higher than the elastic component. Then during the curing, we have a crossing of these two components, and then finally our material has elastic component is higher than the viscous component, and it means that material is not liquid anymore, it is elastic or maybe vitrified. And here the crossing point is a gel point. And this gel point allows us to find, just to compare this data with DSC data and to find at which degree of conversion we have a gel point where we have a gelation. And after that, we can use this degree of conversion for gel point for our simulation and for the predictions. Now we have data and we can create a kinetic model. Firstly, the kinetic model is based on Arrhenius equation. We have classically reactant product activation energy over transition state. We have enthalpy of reaction. We have everything is based on Arrhenius equation with pre-exponential factor, activation energy, and reaction type. There are two approaches. One is model-free approaches when we have for our kinetic always one kinetic equation. Also, if we have two or many reaction steps, but again, only one kinetic equation is used, and activation energy per exponential factor depends on degree of conversion. Then we have a model-based approach where each step has their own kinetic equation, and the pre-exponential factor and degree of activation energy are independent from a degree of conversion for each individual step. And of course, these values could be different for different steps. And now for curing, especially for curing, now we will speak about a reaction type. For reaction type, it is usually Kamal-Soror equation. And this Kamal-Soror equation has two steps, two parallel pathways. One is the nth order and another is autocatalytical order. And here we have a part which is responsible for autocatalysis. But usually the activation energy for nth order pathway and autocatalytic pathway are the same. And therefore, we have in our KineticsNeo software the simplified version of Kamal-Soror equation where activation energy is the same. Here, activation energy is the same for both pathway. The first one is nth order reaction and another one is our autocatalytic reaction. Additionally, we have BNA, the Proud-Tompkins reaction, where we have only autocatalytic pathway and no nth order reaction. Here, example of kinetic model for epoxy, for curing of epoxy resin. Here is monofunctional epoxy, phenylglycetyl ether with aniline, and we have a measurements with 1 to 2.55 and 10 K per minute. One step autocatalytic reaction of CN type. It's with two pathways with the same activation energy for both pathways and the first order of autocatalysis. Here we have measured and data and simulated data with this model, and we see that one model can good describe all experimental data. Here we have double step model, two component epoxy with two steps. Step A to B here is the first one, B to C is the second one. Our software is able to show each peak, reaction peak for each curing, for each individual step of our curing. And here the peaks are not independent, they are dependent like it shows in our model. Next curing is phenol formaldehyde resin, and it is measured in high pressure crucible in order to avoid a very high endothermal effect of evaporation. Here we have some melting step, maximum step, some shoulder, and then the final curing step, 4 steps. And this 4-step model is able to help us to make predictions for any temperature program. Here we have temperature program, and we have degree of conversion for this temperature program. Here is a share modulus for epoxy resin, which is measured with rheology, typical data. What is important here, we must select tangential baseline and remove a baseline for a reactant and for product. It's not they are not straight lines, they are just the curves depending on activation energy of temperature dependence of viscosity on temperature. And here for several measurements we do the same baselines, and we can create kinetic model. Here one step kinetic model, and we can predict not only degree of conversion or concentration of reactant, we can predict the viscosity. And in this point, we can see when the viscosity is the lowest, when the viscosity is the highest, in order to avoid some problems with the curing of our materials. So here we can just select another temperature program and to remove this low point with the point with very low viscosity of our material. here is data of DEA, dielectric analysis. It's very similar to rheology data. And there are some articles where it is shown that there is a correlation between mechanical viscosity, or dynamic viscosity, for example, dynamic shear viscosity, and dielectrical ion viscosity. And here the method of analysis is exactly the same. The firstly is a baseline for reactant, then for product, and then we have one kinetic equation for description of all of this data. Now we have some example how it was used for a real industrial application. We have a company, Blacks Advanced Materials, Blacks Advanced Composites in Italy, and they produce advanced composite materials, carbon, glass, aramid, and so on. And it works with automotive, sports goods, and airspace sector. And here it was the bike rim. And for this bike rim, a total Q cycle was 12 hours. And finally, in order to get 95% of conversion, it was too long. The question is, could it be shorter to get the same or better part quality? The red curve is a temperature for industrial cycle, and the black curve is our curing curve. Now we have measurements at different heating rates. Then we apply our kinetic modeling for this data. In this case, numerical optimization, model-free optimization was done with one click, and the result has a very high value of R square. Then you make a validation of this model, not for dynamic heating as it was for our modeling, but for isothermal data. And we see that for isothermal data, it is a difference less than, for the worst case, less than half of a minute. So we can use this model. And then we use this model for a real cycle and see where the maximum of curing happens. What should we do to avoid overheating? We can make isothermal patch shorter. And then finally, we have another temperature program, which is a new cycle. And here we have reduced a time from industrial production time from 460 to 280 minutes. And in this case, for the customer, it was a really good decreasing of the production side, and now the costs of the production will be reduced according to this time, short time. Now we have a new models which are taken into account the glass transition temperature. If we below the glass transition temperature, then material could be broken and it is in glassy state, and above glass transition temperature, material is in rubbery or liquid state. And the problem is that the glass transition does not stay at the same position, and for uncured material it has one temperature, and for cured material it has another temperature. If you make the curing analysis, then we must take into account that for glassy state we have slow curing, and for rubbery or liquid state, for temperature above glass transition, we have fast curing. And we must take into account this during simulation, but firstly we must know where is the glass transition for the current degree of conversion. In order to find this dependence, the following measurements normally are done. Firstly, we have heating. Here is a temperature up to some partial curing. Find a glass transition of uncured material, then make cooling and heating again, and then for the partially cured material, we have another value of glass transition, and from the rest curing, we can find the degree of cure which corresponds to this glass transition temperature. And finally, we can find the dependence, how glass transition moves from lower value to higher value with degree of curing here. And now our next, recent study, time temperature transformation cure diagram of epoxy amine system. Here we did a measurement DSC. First measurement has a glass transition almost -40. The second heating for cured material has a glass transition temperature 123. It's really a big difference. But here we are able to find the glass transition only for 4 of these samples, because for other samples, the glass transition is somewhere during the curing. Now we use temperature modulated DST in order to find the glass transition for all 10 samples which are partially cured, and after that we have dependence of the glass transition temperature on degree of conversion. And here are our measured glass transition temperature for each partially cured material. Then here again, total cured and totally uncured. We can put or just fit this data with Di-Benedetti equation inside our software. And then we have a parameters of Di-Benedetti equation, and we will use this equation inside the software in order to find what is the current degree of what is the current glass transition temperature for the current degree of cure during the whole cured process. And if we above it, then reaction goes fast. If we below, then reaction goes slow. What is inside our software? Here we have a dependence on temperature and the reaction type, which is Kamal-Thorov. If we much below glass transition, then we have Arrhenius equation with the low pre-exponential factor A. If we much above glass transition, then we have again Arrhenius equation, but with a high pre-exponential factor, the same activation energy, which depends on the nature of our material. And if we somewhere in the middle, then our K reaction rate depends on 2 parts. The first one is a chemical part, which is just a normal Arrhenius equation. And the second part depends on diffusion, and it depends on diffusion according to Williams-Landau with some constants, T1, T2, which are unknown. And this is the mathematics inside the software. You can calculate, of course, manually. It costs you several days for evaluation of each curve. Here in the software, we just make one-click diffusion control. And after optimization, we have this value C1, C2, and the initial value of diffusion factor, which are found for the best fit of between our model and our experimental data. Now we have this data, and we can start to make the time temperature transformation diagram. But for this case, it is necessary to have a gelation, GIL point. We make a measurement, rheological measurements with oscillating parameter, and we have found a GIL point during the heating. And this heating was done with 3 K per minute. And then we compare this data with DSC data with the same heating rate. And we can find from DSC data with the same temperature conditions that for this temperature we have a 67% of conversion. And it means that for our system, chemical system, GIL points corresponds to 67% of conversion, and we can use this value for the simulation of our time temperature transformation diagram. Here in the software, we just select this diagram for simulation, and we have several parts. The first part is the glass transition for uncured material. Below this temperature, we have totally uncured material. Here we have a glass transition temperature for totally cured material. Above this temperature, we have always totally cured material. Then we have gelation curve. This one, the violet curve here, which means the gelation point. Here, from the beginning up to gelation curve, we have a viscous liquid. Between gelation curve and vitrification curve, we have elastic state of material. And after vitrification, we are below glass transition and we have a glassy state. And with this diagram, we can read what time is necessary for us for isothermal conditions for the crossing of our gelation time, gelation curve and vitrification curve. For example, here for the given temperature, isothermal temperature for many days, we can find at which point, at which time we have gelation and changing from viscous liquid to elastic, and at which time point we have a changing from elastic to glassy state. And now, of course, we must validate this process. We did the following really long measurement. We put our two-component system at room temperature for 5 days. And after that, after these 5 days, we make a measurement in order to find what is the glass transition for this partially cured material and what is degree of conversion for this partially cured material. And we have found that the glass transition and conversion for this long validation time are in agreement with our predictions according to time temperature transformation diagram. So this diagram works and we can use it in order to find how the curing goes on and where is the glass transition and gelation point. And now a very nice part is dependence on additional parameter. Here we speak about UV curing, the curing of under UV light. And here the measurements are done under dielectric analysis with the frequency 10 kilohertz. We make a measurement for one constant value of UV intensity, 75 milliwatt per square centimeter at the temperature 39 to 150 degrees C. And we have some model. But if we take a constant temperature but different intensities, then we can see that reaction rate is also different. The slowest one for the lowest value of intensity for 36, and the fastest one is for highest value of intensity. And in our software, we are able to create one common kinetic model, which shows how our curing rate depends on temperature and on UV intensity. And here are our results, and you see that the simulated, the experimental data and our model are mostly in agreement with each other. Next point, our next example is really new. Here we can find how the reaction rate, curing rate depends on the different concentration ratios. Here we have a data for our analysis. We have 3 different ratios, 1:1, 1:2, and 2:1. It's a ratio of epoxy to aniline. And for each ratio, the measurements are done for 1, 2.5, 5, and 10K per minute. And if we compare this data for different ratios, then we can see that the point of maximum, for example, for 10K per minute, has totally different temperature. Here is 180 degrees C, here is 194, and for epoxy to aniline ratio 2:1, we have 207 degrees C. So the ratio, the position of the peaks is totally different. The concentration has the influence on the reaction rate. It is the first point. The second very interesting part, if we compare the shape of the curve. The shape of the curve, for example, for 10K per minute is totally different. At the beginning, it is more or less the same, but the final part is different. Here, for 1 to 2, the final part is more sharp. For 2 to 1, orange is also sharp, but for 1 to 1, this final part is really very, very slow. Why? Here we have the concentration ratios, which are close to the optimal values, and then we have the total reaction, the total order of reaction, like a sum of the first order regarding the first reactant and the second order regarding to the second reactant. But if we have another concentration ratio, then we have a high excess, and then the changing of the concentration for the reactant with high excess has almost no influence on the order of reaction. Now we can make some preliminary analysis of each ratio of reactants, and we can find that the activation energy everywhere is the same. It depends on the nature of reacting materials, but the pre-exponential factor is totally different, and the reaction order is also different. It is from 1.0 to 1.8. It is almost twice higher, and here we have 1.1. And now we can just use the new version of our kinetics now and make not a separate analysis for each ratio, but the total analysis for all ratios and for all heating rates. And now we have all 12 curves with the ratio 1 to 1, 1 to 2, and 2 to 1. And for all heating rates from 1 to 10 for each concentration ratio, and we have one model which can describe all curves with different heating rates and different concentration ratio of our reactants, epoxy and aniline. That is the first picture, and a second picture shows the peak area, the enthalpy of our reaction, and we can find that the highest is for 1 to 1, where we have almost optimal ratio of the concentration of both reactants. And if one of them has excess, then it reacts not completely, and we have the peak area and enthalpy of reaction is lower than it should be for the optimal value. So we can see that our model can describe everything, the heat flow, and it could also describe the enthalpy of reaction. And the final part is our Thermica software, which can make a simulation of the peak volumes, including the production of the energy and some overheating for the peak volume somewhere in the middle. For example, the first picture has a temperature, the second has a degree of conversion, and the last one has the conversion rate of conversion. We can have some geometry, a different temperature from different sides, We can have a different material from the different site with different thermal conductivities. We can use a different container values, or for example, some substrate on the bottom. And this substrate can has different material which is selected from the library, and we can select also the thickness of this material, and after that we can make a calculation. For each point of our geometry, we can calculate a temperature. For example, here and here we have some increasing of a temperature because of the exothermal curing reaction. We can also select a different point on a radial direction. We can show the temperature. We can show the dependence on time for temperature, conversion rate, concentration, for multi-step reactions. And now what is especially for the curing process. Here we have a material for the cross-section, horizontal and vertical cross-section. And here we have a glass transition. It means that if you have from Kinetics Neo one model, kinetic model with diffusion control near the glass transition, which includes vitrification process, then you can take this model, load it into Thermica Neo software, and here you make prediction not only the temperature and the concentration, but the glass transition temperature. And here, for example, we can see what is the glass transition temperature in horizontal and vertical cross-section. The next part, which is also very important, especially for the curing, is the changing of the linear size of the polymer. It is known that the polymer will change the linear size, their length during the curing. And here it is very important, for example, for some processes like lamination, because delamination can happen. And here in our software, we can simulate a changing of the length. We can see what is the length before process, before curing, during the process, and what is the final part. So in this case, you can just make a simulation of the length of your polymer during the curing process. And if you have a different curing, different materials, then you can see what is the changing of the length for one of material and for another of material, and at which temperature everything happens. And again, all information about our software, Kinetics Neo and Thermica Neo software, could be found on our website, here kineticsneo.com. And you can find here user guide, some training examples. Here are our webinars in PDF and video. You can get a trial version for 30 days in order to see if it works good for your application or not. And our Kinetics Neo software is based on the article of ICTAC Kinetic Committee recommendations for multi-step kinetics. Thank you very much. And now, please, questions.
Okay, Elena, thank you for this great presentation. We are still staying for a few minutes to answer your open questions. So I already mentioned it at the beginning. Please let us know any questions you have right now. You are able to type them in to our questions box. It is usually called Q&A area, and the icon looks like a speech bubble with a question mark. You will get our recording in a few days, and even if you have questions afterwards, please feel free to just let us know these questions so we can answer them afterwards via email. I have already posted you our general webinar email address, webinar_ngb@netsch.com, as a message. So please feel free to get in touch whenever you have any questions coming up afterwards. So Elena, I already see two open questions. I would directly start with them and let's see what still will happen. The first question is, can Kinetics Neo analyze not concentration ratio, but also mass ratio? Can you help out here?
Yes, thank you. It's very, very good question, because we know that for some chemical systems, the mole ratios mole values are unknown, and the stoichiometric coefficients are unknown, and the only value which is known is the mass ratio, or the mass of one component and the mass of another component. And our goal in our Kinetics Neo software was to analyze the data for the ratios. And now it is done not only for known mole ratio, but also for known mass ratio. So you can just put that the mass of the first component is 1 milligram, and of the second component is 2 milligram. And after that, the software take this, and then we'll create the kinetic model for this ratio. And here is some internal parameter which is unknown, just to recalculate the mass ratio to the mole ratio. And finally, you will get a kinetic model and this parameter which are recalculated. So yes, it is possible to work with the mass ratio, and finally you will have a possibility to make a simulation for your new mass ratio of the components.
Okay, great. Thank you for this answer, Elena. I go on with the next question because there are some appearing. What references can I use in publication or reports to customers? Can you say something about this?
I think this is our, maybe you see this, my slide. This is the main reference which is used. So all mathematics, including Kamal-Suror equation, including the diffusion control, it is described here in this article. And also the different approaches like model-free, model-based, they are also described in this article. And you can just use this article as your main document for the reference, because here is a lot of information, and here if something written very shortly, then it is enough references in the text of this article to some additional information. So I think it could be nice.
Okay, thank you so much. The next question, what about analyzing materials with multiple exothermic or endothermic peaks?
That was already one example here, I think, at the beginning. And here we have, this one. Here we have the main process with 1, 2, and 3 steps. They are exothermal, and here is endothermal. And in this case, we can use model-based analysis in order to create one model where we have one endothermal peak. And I can tell you that the model-free analysis or isoconventional methods are not work for this case, because they are based on the peaks which have only the same direction. Only, for example, for the curing, all peaks must be exothermal. And if some of them endothermal, then model-based analysis can help you to create a model where one of steps has another direction and has the negative contribution to the total effect. You can make it in our Kinetics Neo software.
Great, thank you so much. That would it be, Elena. I think we can wrap it up for now. No more open questions. To all of our attendees, again, just a hint from my side. after maybe you received our recording and some questions will appear, please always feel free to get in touch with us. The general webinar address is posted as a message. It is called webinar_ngb@netsch.com. So as I said, please feel free to always get in touch with us. Thank you for joining today's webinar. We hope that you find it very informative, and hopefully we see us soon in another webinar. Elena, thank you for this great presentation and enjoy the rest of your day. Bye-bye.
Yeah, thank you, Victoria, and thank to all attendees for your time and for your interest. Thank you. Bye.
Bye.